Hello friends, welcome back to my YouTube channel. In this class I am going to discuss about the thermodynamic temperature scale. What is a thermodynamic temperature scale? A temperature scale that is independent of substances that are used to measure temperature is called thermodynamic temperature scale. Such a temperature scale offers great convenience in thermodynamic calculations. Calculations are bit easier with this thermodynamic temperature scale. In fact, this scale is independent of the properties of substances. And this is based upon one of the corollaries of Carnot's theorem. Before going in detail into this temperature scale, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. You see, what does the corollary of Carnot's theorem states? Corollary of Carnot's theorem. In last class, I have discussed in detail corollary of Carnot's theorem. It says that the efficiencies of all reversible heat engines operating between same two temperature reservoirs are same. So this is a corollary of Carnot theorem. So from this, what we can conclude that suppose this is a source. Source means high temperature reservoir at TH, and this is a sink, low temperature reservoir TL, and this is a heat engine, Carnot heat engine or reversible heat engine, and it is a clockwise device, power producing device. Suppose this is QH amount of heat is added to heat engine from the source, and QL is the heat rejected by the heat engine, and this is suppose work output of this reversible heat engine. Efficiency of any reversible heat engine only depends upon the temperatures of both source and sink and on nothing else. It does not depend upon the amount or nature of working substance undergoing the cycle, nor even on the manner in which the cycle is executed. All the processes within the cycle are executed. It does not depend on anything. Efficiency of any reversible cycle working between two temperature limits TH and TL only depends upon two things. First is this temperature TH and this temperature TL. This is obtained from this corollary. This जो conclusion है वो this is obtained from this corollary of Carnot's theorem. Since the efficiencies of all reversible heat engines operating between same temperature levels are same, means the efficiency of any reversible engine only depends upon the two temperature limits and nothing else. So what I can write is thermal efficiency. In fact, efficiency here refers to thermal efficiency. Efficiency of any reversible engine, suppose this reversible heat engine, depends upon only TH and TL and nothing else. So this can be described as a function of TH and TL. Suppose this function is G of TH and TL. This function is G. If QH amount of heat is added to the heat engine from source and QL heat is rejected by this heat engine to the sink, which is at the temperature TL, then what is the efficiency of this heat engine cycle. We know that efficiency of any heat engine cycle is 1 minus heat rejected, which is in this case is QL, divided by QH. Because efficiency of any cyclic heat engine is net work output divided by heat supplied, and from first law we can also find out that the efficiency of any heat engine is 1 minus heat rejected divided by heat supplied or heat added. So here in this case heat supplied is QH, and QL cannot be 0. If QL is 0 means it is violative of Kelvin-Planck statement, and the whole amount of heat that is supplied cannot be completely converted into work output. So 1 minus QL by QH is the efficiency of this reversible heat engine, which is equal to, suppose, G of TH and TL, which we have already taken. So from this, what I can write is QL divided by QH is, suppose, another function G dash of TH TL. And from this, I can also write like this: QH upon QL is, suppose, another function F of TH and TL. So this QH by QL is a function of TH and TL only, where QH is the heat coming from the high temperature reservoir, that is source, which is at temperature TH, and QL is the heat rejected to low temperature reservoir, which is at temperature TL. QH upon QL, or the ratio of QH and QL, is a function of TH and TL only. So suppose there are, so you can take this as equation 1. Suppose this is your equation 1. Suppose there is a high temperature reservoir which is at T1, high temperature reservoir, temperature or high thermal energy reservoir, high temperature reservoir or source, and there is a reversible heat engine. Suppose reversible heat engine, suppose A, this is heat engine A, is operating between this high temperature reservoir, and the amount of heat that is extracted by this engine from this high temperature reservoir is, suppose, Q1, and this produces work WA. Suppose heat rejected is Q2, and this temperature, this intermediate temperature, is, suppose, T2, and same amount of heat is also, this T2 is a sink for this engine A. This T2 is a sink for this engine A, and source for another engine, suppose B, suppose reversible heat engine B, and heat is same heat, whatever heat is rejected to this T2 by reversible heat engine A is again supplied to this reversible heat engine B. This Q2 is the heat added to reversible heat engine, and T2 becomes source for second heat engine, that is heat engine B, and it is already a sink for heat engine A. So when this happens, this we can say that these heat engines A and heat engine B are operating in series. These two reversible engines or Carnot heat engines are operating in series. Suppose the work delivered by this heat engine is WB, and suppose Q3 is the heat rejected by this heat engine B to sink. This is T3, sink, or you can say low temperature reservoir. So these A and B are two Carnot engines operating in series. Suppose another, at the same time, another heat engine that is C. Suppose this is, all these are cyclic devices, clockwise devices. So another reversible heat engine, suppose C, operates between same two temperatures T1 and T3, and Q1, suppose both these heat engines A and C are getting same amount of heat from the source Q1, and if the efficiency of this heat engine, combined reversible heat engine, will be same as the efficiency of this reversible heat engine C, since both are operating between the same two temperatures, that is T1 and T3. If you combine this reversible heat engine A and B together, then efficiencies of this combined reversible heat engine will be same as the efficiency of this heat engine C, since both this combined heat engine operates between T1 and T3, and heat added here is Q1, here heat added is Q1. So obviously heat rejected will be also Q3 for engine C also. So now the efficiency of this combined reversible heat engine A and B put together will be equal to the efficiency of reversible heat engine C, since this combined heat engine operates between T1 and T3, and this reversible heat engine C also operates between T1 and T3. And since heat supplied is same and efficiencies are same, then heat rejected will also be same, Q3. Here the heat rejected by this combined heat engine is Q3, and here it will also be Q3. So applying equation equation 1 to all the three engines A, B and C, all three engines separately. We have now three engines A, B and C. So applying equation 1. Equation 1 is QH by QL is equal to F, TH and TL. So heat supplied and heat rejected from high temperature source and to low temperature sink, the ratio of that is only a function of those two temperatures. We have already got it in the form of equation 1. So now for the engine A, it is Q1 by Q2 is a function of T1 and T2. Same equation 1 will be written for each of the three engines. So for the engine A, this is the equation, and for engine B, Q2 by Q3 will be F T2 T3, and Q1 for C, Q1 by Q3 is equal to F T1 T3. Q1 by Q3 is F T1 T3. You see here Q1 by Q2 is function of this temperature T1 and T2. Q2 by Q3 this function of temperature T2 and T3, and Q1 by Q3 for this reversible heat engine C is a function of this temperature and T3. Since reversible heat engine C operates between these two temperatures, so Q1 by Q3 is T1 by a function of T1 and T3, and for heat engine A, Q1 by Q2 is function of T1 and T2. Q2 by Q3 for engine B, reversible heat engine B, is a function of T2 and T3. So then these equations are just based upon that equation 1, and this equation for engine A, this equation for engine B, and this is for equation 3. Let's consider the identity. You see Q1 by Q3 is equal to Q1 by Q2 into Q2 by Q3. There is nothing wrong in this. This is the identity we know. Q1 by Q3 is equal to Q1 by Q2 multiplied by Q2 by Q3. So which corresponds to F T1 T3 is equal to, in place of Q1 by Q3 I can write F T1 T3, in place of Q1 by Q2 I can write F T1 T2 multiplied by F of T2 T3. F are functions. So you see, now from this relation, left hand side is a function of T1 and T3 only. No T2 is there. But right on the right hand side, T2 is there. So right hand side should also be a function of T1 and T3 only, and there should not be any T2 on the right hand side. So how can this be possible? This is only possible if F T1 T2 is represented by another functional form like this. Phi of T1. Phi of T1 is another function of T1 divided by phi of T2. And F, in place of F T2 T3, if I write phi of T2 divided by phi of T3, and on being multiplied, this when multiplied by this, phi T2 will be cancelled out, and whatever will remain is phi T1 upon phi T3, which is F of T1 and T3. So from this I can write Q1 by Q3 is equal to, in place of Q1 by Q2 I will write F T1 T2. From this Q1 by Q3 is equal to Q1, in place of Q1 by Q2 I will write F T1 and T2, and which is nothing but phi T1 divided by phi T2, phi T2 multiplied by F, in place of F T2 T3, phi T2 divided by phi T3. So this is equal to phi T1 divided by phi T3. And Q1 by Q3 is nothing but F of T1 T3 is equal to phi T1 divided by phi T3. And suppose this is equation 2. This is equation 2. From this you see Q1 by Q3 is nothing but, this is Q1 is QH, I can say. QH means heat added to the heat engine from high temperature reservoir, and in place of Q3 I can write QL, because for this reversible heat engine C हो और या combined heat engine A and B put together हो, दोनों केस में QH is Q1 and QL is Q3. So Q1, in place of Q1 I can write QH, and in place of Q3 I can write QL, क्योंकि ये सोर्स से जो हीट आ रहा है QH है और इस सिंक को जो हीट जा रहा है QL. हीट एडेड इज QH फ्रॉम हाई टेम्परेचर रिजर्वर, QL जो है वो हीट रिजेक्टेड टू लो टेम्परेचर रिजर्वर है. So for that I can write Q, in place of Q1 by Q3 I can write QH divided by QL, क्योंकि in this case QH is Q1 and QL is Q3. So QH by QL is phi of TH, high temperature reservoir, divided by phi or TL. This is equation 3. What we found is this heat added, ratio of heat added and heat rejected, heat added from the source to the heat engine divided by heat rejected by the heat engine to the sink is nothing but function of TH divided by function of TL. Phi TH is only a function of TH only, and phi TL is a function of TL only. No other terms are there in the function. So phi TH upon phi TL. Phi can be any function of TH or any function of TL, but this can be any function. There is no restriction on it. But Lord Kelvin first proposed a function to define a thermodynamic temperature scale. And he proposed a function phi t is equal to T, which is absolute temperature. T is the absolute temperature expressed in terms of Kelvin. So he proposed this function phi t is equal to the absolute temperature. So what I can write is QH divided by QL, and this is applicable only for reversible heat engines, not for any heat engine. For any reversible heat engine where QH is the heat added from source and QL is the heat rejected to sink is equal to, in place of phi TH I will write simply TH, क्योंकि phi T is equal to T as proposed by Kelvin. So in place of phi TL, I will write TH upon TL, where TH is the absolute temperature of the source in terms of Kelvin and TL is the absolute temperature of the sink in terms of Kelvin. So this is your equation 4. And this temperature scale is called Kelvin scale. This temperature scale is called Kelvin scale. And the temperatures on this scale are, absolute temperatures. But this relation is obtained. But how can we use this for temperature measurement? It simply says that the ratio of heat added and heat rejected by heat added from source to a heat engine and heat rejected by heat engine to sink is nothing but ratio of two temperatures and expressed in terms of Kelvin. Suppose this is high temperature reservoir at TH and this is low temperature reservoir TL, and a reversible heat engine operates, and this is QH heat RI and QL heat rejected RI. Then I can say that QH divided by QL, if it is reversible only, so this is equal to TH divided by TL, where TH is expressed in Kelvin, TL is expressed in Kelvin. So how to measure the temperature? That is an important question. How to measure the temperature? So from the relation QH upon QL is equal to TH upon TL. So how we can use this equation for temperature measurement? So for that we need a reference point. And in the International Conference on Weights and Measures, which was held in 1954, triple point of water, which is 0.01 degrees Celsius or 273.16 Kelvin, was adopted to be a reference point. And 1 Kelvin is actually 1 upon 273.16 of difference between the absolute zero and the triple point temperature of water. And 1 Kelvin is also equal to 1 degree Celsius. So what is actually 1 Kelvin? It is equal to 1 degree Celsius, and you can also define it as 1 upon 273.16 of difference between absolute zero temperature and that of triple point of water. What is triple point of water? Triple point of water is a temperature at which three phases of water, that is ice, liquid water, and water vapor, and water vapor. Three phases of water coexist. Three phases of water coexist in equilibrium. So that is the temperature. That is 0.01 degrees Celsius or 273.16 Kelvin. So if we operate a reversible heat engine, suppose this is the temperature to be measured. This temperature is to be measured, unknown temperature to be measured, and we operate a heat engine. Suppose this is Q and this is your Carnot heat engine or reversible heat engine. This is the work produced by the Carnot heat engine, and this is triple point of water or TT, and this is suppose QT. From this thermodynamic temperature scale, just this QH by QL is equal to TH by TL. What I can obtain is Q divided by QT is equal to T divided by TT. TT is nothing but the triple point of water. From this I cannot, because since it is a reversible heat engine, this relation will be valid for this reversible heat engine. Q by Qt is equal to T upon Tt. T is the temperature to be measured. From this what I can obtain is Q upon Qt multiplied by Tt. This is triple point of water. So this is Q upon Qt multiplied by 273.16. So this is the formula that can be used to find out the temperature. If we operate a reversible heat engine and measure this amount of heat that is added to this heat engine from an unknown temperature T, and calculate or find out the heat rejected to this triple point of water, then I can obtain this temperature T. From this equation, where Tt is 273.16 Kelvin. When it is multiplied with this ratio of heat absorbed and heat rejected, that yields the unknown temperature T, which is required to be measured. So this is how temperature measurement is done. So thanks for watching.